Imagine standing at the edge of our solar system and looking out into the endless black. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. The darkness stretches in every direction, dotted with distant suns that have burned for billions of years. Each tiny point of light holds secrets we could barely dream of just 30 years ago. In 1995, two Swiss astronomers changed everything we thought we knew about planets. Mitchell Mayer and Didier Queloz pointed their telescope at a star called 51 Pegasi, 50 light years from Earth. They discovered something that should not have existed. A planet larger than Jupiter was racing around its star in just 4 days. This world, now called 51 Pegasi b, became the first confirmed planet orbiting a sun-like star beyond our own. The discovery shattered our understanding of how solar systems form. For centuries, we assumed all planetary systems looked like ours. Small rocky worlds close to the star, giant gas planets farther out. But 51 Pegasi b was a massive gas giant hugging its star so tightly that its surface temperature reached 1,800 degrees Fahrenheit. The planet completes an orbit faster than most people take a vacation. This strange new world opened the floodgates. Within a decade, astronomers found hundreds more planets circling distant stars. Each discovery revealed how wonderfully diverse planetary systems could be. Some planets orbit 2 stars at once, experiencing double sunsets like the fictional world of Tidally. Others spin backwards compared to their star's rotation, suggesting violent collisions in their past. The numbers grew quickly. By 2009, NASA launched the Kepler Space Telescope, designed specifically to hunt for planets. Kepler stared at a small patch of sky containing 150,000 stars. It watched for the tiny dimming that occurs when a planet passes in front of its star. This method, called the transit technique, revealed planets we never could have imagined. Kepler discovered worlds made entirely of diamond. Planets where it rains molten glass sideways in 700-mile-per-hour winds. Ocean worlds completely covered in water hundreds of miles deep. rocky planets so close to their stars that their surfaces are lakes of lava. Each new world expanded our sense of what was possible in the universe. Today, we know of more than 5,000 confirmed planets orbiting other stars. These exoplanets, as astronomers call them, come in sizes and types that don't exist in our solar system. Super-Earths are rocky worlds up to 10 times more massive than our home planet. Mini Neptunes are smaller versions of our ice giant neighbors. Hot Jupiters are gas giants that orbit their stars in days rather than years. The diversity is staggering. Some planets are so dark they absorb almost all light that hits them, appearing blacker than coal. Others reflect light so efficiently they shine like polished mirrors. There are planets with atmospheres made of vaporized rock, and worlds where the pressure is so intense that carbon crystallizes into diamond rain, falling through hydrogen skies. Perhaps most remarkable are the planets that might harbor life. Scientists estimate that 1 in 5 sun-like stars hosts an Earth-sized planet in the habitable zone. This is the region around a star where liquid water could exist on a planet's surface. Not too hot, not too cold, but just right for the chemistry of life as we know it. The closest potentially habitable world sits just over 4 light-years away. Proxima Centauri b orbits our nearest stellar neighbor, a small red dwarf star. This planet receives about the same amount of energy from its star as Earth gets from the sun. Whether it has an atmosphere, oceans, or any form of life remains a mystery that future telescopes might solve. Every new discovery connects back to the same profound truth. Planets are not rare cosmic accidents. They are common, diverse, and scattered throughout the galaxy like seeds on fertile ground. Our Milky Way contains at least 100 billion stars, and most of them likely host planetary families of their own. The universe has been conducting experiments in world building for over 13 billion years. Each star system represents a different attempt at creating the conditions for complexity, chemistry, and perhaps even life. Some experiments produce scorching hellscapes. Others craft frozen ice balls. A precious few might create worlds where liquid water flows and life takes hold. As we drift off to sleep tonight, thousands of worlds orbit distant suns in the darkness above us. Each one tells a story of cosmic forces, stellar evolution, and the endless creativity of a universe that never stops surprising us with its capacity for wonder. Finding planets around distant stars presents one of astronomy's greatest challenges. These worlds shine only by reflected starlight, making them billions of times fainter than their host stars. Imagine trying to spot a firefly hovering next to a lighthouse beam from 1,000 miles away. That captures the difficulty astronomers face when hunting for exoplanets in the cosmic darkness. The first successful method relies on a planet's gravitational pull on its star. As a planet orbits, it tugs its star back and forth in a tiny cosmic dance. This stellar wobble stretches and compresses the star's light waves as they travel toward Earth. When the star moves toward us, its light shifts slightly bluer. When it moves away, the light becomes redder. Scientists call this the radial velocity method, and it can detect wobbles as small as a human walking pace. Mitchell Mayer and Didier Queloz used this technique to discover 51 Pegasi b in 1995, the first confirmed planet orbiting a sun-like star. Their Swiss team measured wobbles in starlight, so precise they could detect changes smaller than the width of a human hair. This discovery opened the floodgates for exoplanet research and earned them the Nobel Prize in Physics. The planet they found shocked everyone. It was a gas giant like Jupiter, but it orbited its star every 4 days instead of 12 years. A second method watches for tiny dips in starlight when planets pass in front of their stars. These events, called transits, block a fraction of the star's light and create a subtle dimming that sensitive instruments can measure. A planet the size of Earth blocks about 1/100th of 1% of its star's light. That's like detecting the shadow of a coin held in front of a car's headlight from several miles away. NASA's Kepler Space Telescope perfected this transit method and revolutionized our understanding of planetary systems. Launched in 2009, Kepler stared at a single patch of sky containing 150,000 stars for nearly 4 years. It discovered over 2,600 confirmed planets and identified thousands more candidates awaiting verification. The telescope could detect planets smaller than Earth and track their orbital periods with extraordinary precision. Transit observations reveal far more than just a planet's existence. The depth of the dimming tells us the planet's size relative to its star. The time between transits reveals the orbital period and distance from the star. Some planets show additional dimming patterns that indicate the presence of moons, rings, or atmospheric features. Scientists can even analyze starlight filtering through a planet's atmosphere during transit to identify specific gases and chemicals. Direct imaging represents the most challenging but potentially rewarding detection method. Astronomers use special instruments called coronagraphs to block a star's overwhelming glare and reveal the faint light from orbiting planets. This technique works best for young, hot planets that still glow with heat from their formation. The first directly imaged exoplanet, 2M1207b, was discovered in 2004, orbiting a brown dwarf star 170 light-years away. Ground-based telescopes employ adaptive optics systems that use flexible mirrors to counteract atmospheric turbulence. These mirrors adjust their shape hundreds of times per second, guided by laser beams shot into the upper atmosphere. The result is images nearly as sharp as those from space telescopes. The Very Large Telescope in Chile has directly photographed several multi-planet systems using these advanced techniques. Gravitational microlensing offers another window into distant worlds. When one star passes precisely in front of another from Earth's perspective, the foreground star acts like a cosmic magnifying glass. Its gravity bends and focuses the background star's light, creating a temporary brightening that can last days or weeks. If the lensing star has planets, they create additional spikes in the light curve that reveal their presence. This method excels at finding planets far from their stars, in regions where other techniques struggle. Microlensing has discovered planets orbiting stars near the center of our galaxy, over 20,000 light-years away. Some of these events reveal free-floating planets that have been ejected from their original star systems and now wander through interstellar space alone. Modern planet hunters combine multiple detection methods to build complete pictures of distant worlds. The transiting Exoplanet Survey satellite, launched in 2018, monitors the entire sky for transit signals. Ground-based telescopes follow up with radial velocity measurements to confirm discoveries and determine planetary masses. This coordinated approach has accelerated the pace of discovery to several new planets each week. Each detection method has strengths and limitations that complement the others. Transit surveys excel at finding planets close to their stars, but miss those in wider orbits. Radial velocity measurements work best for massive planets, but struggle with Earth-sized worlds. Direct imaging captures planets in distant orbits, but requires special conditions. Together, these techniques paint an increasingly detailed portrait of the planetary population throughout our galaxy. The story of habitable zones begins with a simple truth that governs all life as we know it. Water must exist as a liquid, not frozen solid like the ice caps of Mars, not boiled away like the vanished oceans of Venus. Liquid water flows, dissolves nutrients, and allows the complex chemistry that builds living cells. This narrow requirement creates invisible boundaries around every star in the universe. Astronomers call this special region the habitable zone, though many prefer the nickname that captures its essence perfectly. The Goldilocks zone. Not too hot, not too cold, but just right for liquid water to pool on a planet's surface. The zone exists because stars pour energy into space at different rates, and planets orbit at different distances. Move too close to the star, and any water boils away into steam. Drift too far out, and water freezes into solid ice that never melts. Our own solar system demonstrates this principle with stark clarity. Venus orbits just inside the inner edge of our Sun's habitable zone. The extra heat from being slightly closer triggered a runaway greenhouse effect billions of years ago. Carbon dioxide built up in Venus's atmosphere until surface temperatures reached 900 degrees Fahrenheit. hot enough to melt lead. Mars sits near the outer edge of the zone, where the sun's warmth grows too weak to keep water liquid on the surface. Ancient riverbeds carved into Martian rock tell us water once flowed there. But the planet lost most of its atmosphere and grew too cold to sustain liquid seas. Earth orbits in the sweet spot between these extremes. Our planet receives just enough stellar energy to keep vast oceans liquid while avoiding the scorching fate of Venus. This perfect positioning allowed life to emerge in Earth's early seas and flourish for billions of years. The habitable zone around our sun extends from about 0.95 astronomical units to 1.37 astronomical units. Earth sits comfortably at 1 astronomical unit, the distance we use to measure all other planetary orbits. The width and location of habitable zones depend entirely on the star at the center. Massive, brilliant stars burn through their fuel quickly and shine with intense blue-white light. Their habitable zones stretch much farther from the star because of the tremendous energy output. A star 10 times more massive than our sun might have a habitable zone extending from 3 to 6 astronomical units. But these stellar giants live fast and die young, burning out in just a few million years. Not nearly enough time for complex life to evolve on any orbiting planets. Red dwarf stars tell a different story. These small, dim stars burn their fuel so slowly they can shine for trillions of years. Their habitable zones huddle close to the star, sometimes closer than Mercury orbits our sun. A planet in a red dwarf's habitable zone might complete an orbit in just a few Earth days. The star's weak light means planets must stay close to receive enough warmth for liquid water. Red dwarfs make up about 75% of all stars in our galaxy, making their compact, habitable zones prime real estate for potentially habitable worlds. The habitable zone concept grew more complex as scientists learned about planetary atmospheres and greenhouse effects. A thick atmosphere can trap heat and extend the outer boundary of the zone. Venus proves that too much atmosphere creates a hellish greenhouse. But Mars shows that too little atmosphere lets heat escape to space. The right atmosphere atmospheric pressure and composition can keep water liquid even at distances where it would normally freeze. Scientists now recognize that the habitable zone shifts over time as stars age and change. Young stars often flare with violent bursts of radiation that could strip away planetary atmospheres. As stars mature and settle into steady burning, their habitable zones stabilize. Our sun has grown about 30% brighter since Earth formed 4.6 billion years ago. The habitable zone has slowly moved outward, and Earth has stayed within it, partly because our atmosphere evolved to compensate for the increasing solar energy. The discovery of thousands of exoplanets has revealed habitable zones around every type of star. Some planets orbit binary star systems, experiencing complex patterns of heating as they circle two suns. Others follow highly elliptical orbits that carry them in and out of their star's habitable zone during each planetary year. These varying conditions create a rich diversity of potentially habitable environments throughout the galaxy. Each habitable zone represents a cosmic cradle where the conditions for life might take hold. The gentle warmth that allows water to flow, the stable energy that permits complex chemistry to unfold over billions of years. These invisible boundaries around distant stars mark the places where other worlds might harbor their own stories of life, emerging from primordial seas. Among the first exoplanets astronomers discovered, a strange class of worlds challenged everything we thought we knew about planetary formation. These giants, now called hot Jupiters, orbit so close to their parent stars that they complete a full year in just a few Earth days. Imagine a planet the size of Jupiter, with its swirling storms and massive gravitational pull, racing around its star in less time than it takes our moon to circle Earth once. These scorching worlds shouldn't exist where we find them. Jupiter-sized planets form far from their stars, where temperatures stay cold enough for water and other compounds to freeze into solid ice. This ice provides the building material that gravity needs to construct such massive worlds. Yet, hot Jupiters orbit their stars at distances closer than Mercury, circles our sun. The intense stellar radiation heats their atmospheres to temperatures exceeding 2,000 degrees Fahrenheit. At these extreme temperatures, metals like iron and titanium exist as vapor in their skies. The mystery deepened when astronomers realized these planets must have formed much farther out, then somehow migrated inward toward their stars. The journey inward transforms these worlds completely. As they spiral closer to their parent star, the intense heat begins to strip away their outer atmospheres. Some hot Jupiters lose material so rapidly that they leave behind glowing trails of escaping gas, like cosmic comets made of vaporized rock and metal. The building blocks of these migrating giants tell stories written in starlight. Their atmospheres contain the same elements that formed in the hearts of ancient stars billions of years ago. Iron forged in stellar cores and scattered across space when massive stars exploded as supernovas, now floats as metallic clouds in these alien skies. Titanium, created in the nuclear furnaces of dying stars, forms exotic compounds that give some hot Jupiter atmospheres their distinctive colors when viewed through powerful telescopes. Water vapor, that precious molecule essential for life as we know it, exists in the atmospheres of many hot Jupiters, despite the extreme heat. This water originally condensed from the same primordial cloud of gas and dust that formed the entire planetary system. The hydrogen in this water was born in the first moments after the Big Bang, while the oxygen formed much later inside massive stars. Even in these hellish environments, the fundamental ingredients of life persist, though in forms far too extreme to support biology. The intense stellar winds from their nearby stars constantly bombard these planets with charged particles. This radiation strips away lighter elements like hydrogen and helium from their outer atmospheres, while heavier elements like iron and magnesium remain behind. Over millions of years, this process gradually changes the composition of the entire planet. Some hot Jupiters may eventually lose so much of their gaseous envelope that only their rocky cores remain, creating a new class of super-Earth planets. The magnetic fields of hot Jupiters interact dramatically with their their stars' magnetic fields. As these massive worlds orbit so close to their parent stars, their magnetic field lines become twisted and stretched. This creates powerful electrical currents that flow between the planet and star, generating radio emissions that astronomers can detect from Earth. These magnetic interactions also accelerate particles to incredible speeds, creating aurora displays far more spectacular than anything seen on Earth. The gravitational dance between hot Jupiters and their stars gradually changes both worlds over time. The planet's gravity raises tides on the star's surface, while the star's gravity stretches and heats the planet's interior. This tidal heating keeps the planet's core molten and active, driving powerful convection currents that generate strong magnetic fields. The same gravitational forces that created the beautiful rings of Saturn and carved the intricate patterns in asteroid belts continue to shape these distant worlds. Some hot Jupiters orbit their stars in the opposite direction from the star's rotation, suggesting violent encounters with other planets during their inward migration. These backward orbits indicate that planetary systems can undergo dramatic reorganization, with massive worlds changing places and smaller planets being ejected into interstellar space. The silicon and carbon in their rocky cores, the sulfur compounds in their clouds, and the trace metals in their atmospheres all originated in stellar furnaces scattered across our galaxy. Each hot Jupiter represents a cosmic laboratory where extreme conditions create chemistry impossible anywhere else. The intense heat and pressure forge new molecular compounds that exist nowhere in our cooler solar system. These alien worlds remind us that the same fundamental elements that built Earth and sparked life here continue to create new forms of matter and energy throughout the universe, connecting every distant planet to the stellar processes that forged the building blocks of existence itself. Beyond the of hot Jupiters lies another class of worlds that challenges our understanding of planetary formation. Super-Earths stretch across the cosmos in vast numbers, worlds larger than our home planet, but smaller than Neptune. These mysterious planets range from 1.5 to 10 times Earth's mass, creating gravitational fields that would crush a human visitor, but might cradle entirely different forms of life. The gravitational forces on these massive worlds shape everything from their atmospheres to their geological activity. A super-Earth with 3 times our planets mass pulls with 3 times the gravitational strength, creating surface pressures that compress rock and metal into forms we barely understand. This intense gravity holds thick atmospheres close to the surface, trapping heat and creating greenhouse effects that can turn ice into steam or forge diamond from carbon deep underground. The same gravitational pull that keeps these dense atmospheres from escaping into space also drives powerful tectonic forces through the planet's interior. Beneath the surface of these worlds, the crushing weight of extra mass creates temperatures and pressures that transform ordinary materials into exotic states of matter. Scientists believe that super-Earths might contain layers of supersonic ice, where water molecules break apart under extreme pressure to create a substance that conducts electricity like metal while remaining solid like ice. The cores of these planets experience pressures millions of times greater than Earth's surface, hot enough to melt iron and dense enough to compress carbon into crystalline structures harder than any diamond. The magnetic fields generated by super-Earths dwarf our planet's protective magnetic bubble. The combination of massive iron cores, rapid rotation, and powerful convection currents creates magnetic fields that extend far into space, deflecting cosmic radiation and solar wind with incredible force. These magnetic shields can stretch millions of kilometers beyond the planet's surface, creating auroras that dance across skies filled with gases unknown on Earth. The interaction between these powerful magnetic fields and stellar wind creates radio emissions that astronomers can detect from thousands of light years away. Heat flows differently through these massive worlds, driven by gravitational forces that compress and stretch the planet's interior like a cosmic accordion. The extra mass creates more radioactive decay in the core, generating internal heat that keeps the planet geologically active for billions of years longer than smaller worlds. This internal furnace drives volcanic activity that can reshape entire continents, releasing gases that transform the atmosphere over geological time. The pressure at the core boundary reaches temperatures hotter than the surface of the sun, creating convection patterns that churn molten rock through the planet's interior like slow-motion lightning. Tidal forces from nearby stars stretch and squeeze super-Earths in ways that generate even more internal heat. When these massive planets orbit close to their host stars, the gravitational pull creates tidal bulges that flex the planet's rocky shell with each orbit. This constant kneading heats the interior through friction, keeping the planet's core molten and driving geological processes that might otherwise have stopped billions of years ago. The same tidal heating that creates the sulfur volcanoes on Jupiter's moon, Io, works on a much grander scale in these distant worlds. The atmospheric pressure on super-Earths can reach hundreds of times Earth's surface pressure, creating weather patterns driven by forces we can barely imagine. Winds accelerated by the planet's strong gravity can reach speeds that would strip the paint from spacecraft, carrying clouds of vaporized rock and metal across continents. The dense atmosphere acts like a thick blanket, distributing heat from the day side to the night side of tidally locked worlds, creating temperature gradients that drive circulation patterns spanning entire hemispheres. These gravitational and thermal forces work together to create worlds where familiar elements behave in completely alien ways. Water might exist as a supercritical fluid that flows like liquid, but expands like gas. Carbon dioxide could form solid layers under the immense atmospheric pressure, creating landscapes of dry ice mountains under skies thick with metallic clouds. The nitrogen and oxygen that fill our lungs might compress into liquid oceans beneath atmospheres of hydrogen and helium. The same stellar processes that created the calcium in our bones and the iron in our blood continue to forge the heavy elements that build these massive worlds. Each super-Earth represents a natural laboratory where extreme forces test the limits of chemistry and physics, creating conditions that might nurture forms of life adapted to crushing gravity and dense atmosphere. atmospheres. These distant worlds remind us that the universe creates endless variations on the theme of planetary formation, each one shaped by the fundamental forces that govern matter and energy across the cosmos. Stars dance in space, but not the way we might imagine. They wobble back and forth in tiny motions so small that detecting them requires instruments more precise than any scale ever built. When a planet orbits a star, both objects actually orbit around their shared center of mass. The star appears to stay still, but it moves in a gentle rhythm, pulled by the gravitational tug of its invisible companion. This wobble measures smaller than the width of a human hair viewed from a mile away. Jupiter causes our sun to move at a speed of just 28 miles per hour, about as fast as a bicycle rider pedaling through a neighborhood. From the distance of the nearest star, this motion would appear 100 times smaller than the thickness of a dime held at arm's length. Yet, astronomers can measure these microscopic stellar dances with such precision that they detect planets smaller than Earth orbiting stars hundreds of light years away. The radial velocity method, as scientists call this technique, works by watching how starlight shifts color as the star moves toward us and away from us. When a star wobbles toward Earth, its light compresses slightly, shifting toward the blue end of the spectrum. When it wobbles away, the light stretches toward red. These color changes happen at the level of individual wavelengths of light, measured in units called angstroms. 1 angstrom equals 1/10,000,000th of a meter. The shifts astronomers detect often measure less than 1 part in 10 million of the total wavelength. To understand this scale, imagine trying to measure the change in pitch of a car horn. As the vehicle moves toward you at the speed of a crawling ant, the Doppler shift would be real, but detecting it would require ears sensitive enough to distinguish between musical notes that differ by less than 1,000th of a semitone. Modern spectrographs achieve this level of precision by splitting starlight into thousands of individual colors, then comparing each wavelength to reference patterns with extraordinary accuracy. A planet the mass of Earth orbiting a sun-like star creates a stellar wobble of just 20 centimeters per second. This equals the speed of a leisurely walking pace, but measured across distances of trillions of miles. The precision required to detect such motion from interstellar distances pushes the boundaries of what technology can achieve. Atmospheric turbulence, thermal expansion of telescope mirrors, and even the gravitational pull of passing trucks can introduce errors larger than the signals astronomers seek to measure. The most sensitive planet-hunting instruments can detect velocity changes as small as 10 centimeters per second. At this level of precision, the motion of sap rising in trees near the telescope becomes a measurable source of interference. The footsteps of astronomers walking around the observatory register as seismic vibrations that must be filtered out of the data. Even the tidal forces of the moon pulling on the telescope structure create systematic errors that require careful correction. Different types of planets create distinct wobble signatures. A massive planet in a close orbit produces a strong, rapid signal that repeats every few days or weeks. A smaller planet farther from its star generates a weaker wobble with a longer period that might take months or years to complete one cycle. Multiple planets orbiting the same star create overlapping patterns of motion, like multiple dancers pulling their partner in different directions at the same time. The mathematics of extracting planetary signals from stellar wobbles resembles the challenge of identifying individual voices in a crowded room. Computer algorithms analyze years of velocity measurements, searching for periodic patterns hidden within the noise of stellar activity and instrumental effects. A single planet detection often requires hundreds of observations spread across multiple years, with each measurement precise enough to detect motions smaller than the speed of growing grass. Ground-based telescopes achieve their remarkable precision by using laser frequency combs, devices that create perfectly regular patterns of light wavelengths as reference standards. These instruments generate millions of evenly spaced spectral lines, providing a ruler against which stellar motion can be measured. The technology borrows techniques from atomic clocks and quantum physics, applying the most precise measurement methods known to science, to the ancient art of watching the stars. The smallest planets detected through radial velocity measurements have masses just twice that of Earth. These worlds orbit so close to their stars that their years last only a few days, but their gravitational influence still creates detectable stellar wobbles. Each discovery pushes the technique closer to finding true Earth twins, planets with familiar masses orbiting at comfortable distances from sun-like stars. The dance between star and planet continues across the galaxy, waiting for instruments sensitive enough to detect even the gentlest gravitational embraces that bind distant worlds to their stellar companions. Sometimes the universe offers us a perfect alignment. When a distant planet passes directly between its star and Earth, something magical happens. The star's light dims by the tiniest fraction, creating a shadow that travels across space for years or centuries before reaching our telescopes. This shadow carries secrets about worlds we will never visit, painted in the language of blocked starlight. The transit method reveals planets through their silhouettes. When a world crosses its star's face, it blocks a small portion of the star's light, causing a brief dimming that sensitive instruments can detect. A planet the size of Jupiter blocks about 1% of its star's light. An Earth-sized world blocks only 1/10,000th of the light, requiring extraordinary precision to measure. The dimming follows a predictable pattern, starting gradually as the planet's edge touches the star's disk, reaching maximum depth when the planet sits centered against the stellar surface, then slowly brightening as the world completes its journey across the star's face. The shape of this light curve tells us the planet's size with remarkable accuracy. A larger planet creates a deeper, longer-lasting eclipse. A smaller world produces a shallower dip that passes more quickly. The exact timing reveals the planet's orbital period, while the duration of the transit depends on the planet's speed and the angle at which we view its orbit. Planets that graze the edge of their star create shorter, shallower transits than those that pass directly across the center. Multiple transits of the same planet allow astronomers to refine their measurements and search for variations that might reveal additional worlds in the system. Sometimes the timing of transits shifts slightly, pulled forward or delayed by the gravitational influence of other planets. These timing variations can reveal planets too small or distant to create detectable transits themselves. The method has discovered entire planetary systems through the subtle gravitational choreography that governs their orbital dance. The Kepler Space Telescope transformed our understanding of planetary systems by staring continuously at a single patch of sky containing over 150,000 stars. This patient vigil lasted nearly 4 years, monitoring each star for the telltale dimming that signals a planetary transit. The spacecraft detected planets smaller than Mercury and larger than Jupiter, revealing that planetary systems come in varieties our solar system never imagined. Hot super-Earths orbit closer to their stars than Mercury orbits the Sun. Mini Neptunes with thick atmospheres exist in sizes our solar system lacks entirely. Transit observations reveal not just the presence of planets, but their physical characteristics. When starlight passes through a planet's atmosphere during transit, different wavelengths are absorbed by various gases in the atmospheric layers. Water vapor absorbs infrared light at specific wavelengths. Sodium creates absorption features in yellow light. Hydrogen produces signatures across multiple colors. By comparing the depth of transits at different wavelengths, astronomers can identify the chemical composition of alien atmospheres from thousands of light years away. Some planets create transits so deep they can be seen with small backyard telescopes. HD 209,458b, a hot Jupiter orbiting a sun-like star, dims its host star by nearly 3% during each transit. Amateur astronomers regularly observe this world's passages, contributing to professional studies of its atmospheric properties. The planet's atmosphere extends far beyond its solid surface, creating an extended envelope of escaping gas that astronomers can detect as the planet transits its star. The geometry required for transits makes them relatively rare events. Only planets whose orbital planes align almost perfectly with our line of sight create detectable eclipses. For every planet we observe in transit, dozens more orbit their stars at angles that never bring them between the star and Earth. Statistical studies suggest that transit surveys detect only a small fraction of the planets that actually exist around the stars they monitor. Ground-based transit surveys scan millions of stars simultaneously, searching for the characteristic dimming patterns that reveal planetary companions. These surveys use networks of small telescopes distributed around the globe, ensuring continuous monitoring as Earth's rotation carries individual observatories into daylight. The combined observations create an uninterrupted record of stellar brightness changes, capturing transits that might last only a few hours. The most precise transit measurements come from space-based observatories that avoid the blurring effects of Earth's atmosphere. These instruments can detect brightness changes smaller than 1 part in a million, sensitive enough to find Earth-sized planets around sun-like stars. Each photon of starlight carries information about the worlds that briefly interrupt its journey across space, transforming simple shadows into detailed portraits of distant planetary systems. The dance of planets across stellar faces continues throughout the galaxy, creating an endless library of eclipses waiting to be discovered by patient observers who understand the language of dimming stars. Not every planet orbits a star. Deep in the cold darkness between stellar systems, worlds drift alone through space. These rogue planets wander the galaxy without the warmth of any sun, carrying only the fading heat from their formation billions of years ago. Scientists estimate that rogue planets might outnumber the stars themselves, creating a hidden population of worlds that float invisibly through the cosmic void. These orphaned worlds began their existence like any other planet, forming in the swirling disk of dust and gas around a young star. But gravitational encounters with larger planets or passing stars flung them from their birth systems, sending them tumbling into interstellar space. The ejection happens quickly in cosmic terms, sometimes taking only a few million years to complete. Once cast out, these planets begin an eternal journey through the galaxy, following orbits around the galactic center that take hundreds of millions of years to complete. Without starlight to warm their surfaces, rogue planets become frozen wastelands where temperatures drop to nearly absolute zero. The surface of a rogue Earth would freeze solid within a few million years, creating a shell of ice hundreds of miles thick. But beneath this frozen exterior, some rogue planets might harbor surprising warmth. Radioactive elements in their cores continue to decay, generating heat that could maintain liquid oceans beneath the ice for billions of years. Jupiter-sized rogue planets retain their heat much longer than smaller worlds. Their massive size traps the thermal energy from formation, creating a slow cooling process that spans many billions of years. These giant rogues might maintain surface temperatures warm enough to support liquid water for longer than many stars will shine. The thick atmospheres of gas giant rogues act like cosmic blankets, holding in heat and creating greenhouse effects that could sustain temperate conditions in their upper cloud layers. Detecting rogue planets presents enormous challenges because they emit almost no light of their own. Most searches rely on gravitational microlensing, a technique that watches for the brief brightening of background stars when a rogue planet's gravity bends and focuses the starlight. These lensing events last only days or weeks, requiring constant monitoring of millions of stars to catch the fleeting signals. The brightness increase follows a characteristic pattern that reveals the mass and distance of the invisible world, causing the lensing effect. Recent surveys have discovered several rogue planets drifting through our local region of the galaxy. One candidate, located about 20 light-years from Earth, appears to be roughly the size of Jupiter, but radiates heat from its formation like a very faint star. Another detection revealed a rogue planet only 6 times more massive than Earth, making it one of the smallest free-floating worlds ever found. These discoveries suggest that planetary ejection happens frequently during the chaotic early stages of solar system formation. Some rogue planets might not wander alone. Computer simulations show that entire planetary systems can be ejected together, maintaining their orbital relationships even as they drift through interstellar space. A rogue system might contain multiple worlds orbiting a central planet instead of a star, creating a miniature solar system powered only by the fading heat of its largest member. These bound systems would be nearly impossible to detect with current technology, hiding entire families of worlds in the darkness between stars. The space between rogue planets and their nearest stellar neighbors spans distances that dwarf anything in our solar system. A typical rogue planet might be separated from the closest star by thousands of times the distance between Earth and the Sun. At such vast separations, the gravitational influence of nearby stars becomes negligible, allowing rogue planets to maintain stable orbits around the galactic center for the entire age of the universe. Brown dwarfs, failed stars that never ignited nuclear fusion, blur the line between rogue planets and stellar objects. These dim worlds form like stars from collapsing gas clouds, but lack sufficient mass to sustain the nuclear reactions that power true stars. Many brown dwarfs likely host planetary systems of their own, creating hierarchies of worlds orbiting objects that themselves orbit nothing but the galaxy. The distinction between a massive rogue planet and a small brown dwarf becomes a matter of formation history rather than observable properties. As our galaxy continues its ancient rotation, billions of rogue planets drift silently through the void, carrying the frozen remains of atmospheres and oceans from their stellar youth. These wandering worlds represent a hidden chapter in planetary science, demonstrating that the universe contains far more worlds than the ones we see illuminated by starlight. Each rogue planet tells a story of cosmic violence and gravitational chaos. Yet some might harbor the very conditions that could sustain life in the cold depths of interstellar space. The cold depths of space hold more than wandering rogue worlds. Red dwarf stars, the most common type of star in our galaxy, burn with a gentle persistence that puts our sun to shame. These small, cool stars glow with barely 1% of our sun's brightness, yet they will continue shining for trillions of years. While our sun will exhaust its fuel in about 5 billion years, red dwarfs have barely begun their cosmic journey. The smallest red dwarfs could burn for 100 trillion years, outlasting every other type of star by vast margins of time. Around these patient stars, planets orbit in tight embraces that would seem impossible in our solar system. The habitable zone around a red dwarf sits much closer to the star than Earth's distance from the Sun. A planet in the habitable zone of a red dwarf might orbit its star in just 20 to 50 Earth days. This close proximity creates a delicate dance between star and planet that unfolds over cosmic time scales. The planet's year becomes shorter than the seasons we know on Earth. Yet, the star's steady output creates a rhythm that could persist longer than any other planetary system. The gravitational pull between red dwarf and planet creates a slow but inevitable change. Over millions of years, the planet's rotation gradually slows until it becomes tidally locked to its star. One side of the world faces the star permanently, basking in eternal day, while the other side turns away into perpetual night. This process happens to nearly every planet orbiting close enough to a red dwarf to receive liquid water temperatures. The transformation takes time, but red dwarfs have more time than any other stars in the universe. Scientists have discovered that this tidal locking might not doom a planet's chances for life. The boundary between the day side and night side could harbor temperatures perfect for liquid water. Winds in the planet's atmosphere would carry heat from the scorching day side to the frozen night side, creating a twilight zone where conditions remain stable. This eternal sunset region could stretch around the entire planet like a ribbon of possibility. The temperature gradient drives powerful atmospheric currents that redistribute heat and create weather patterns unlike anything on Earth. Red dwarf stars experience their own cycles of activity that pulse through their planetary systems. These stars can unleash powerful flares that temporarily increase their brightness by factors of 10 or more. The flares send waves of radiation and charged particles streaming toward any orbiting planets. A planet's magnetic field and atmosphere determine whether these stellar tantrums prove destructive or merely spectacular. Some planets might lose their atmospheres to repeated flaring, while others with strong magnetic shields could deflect the worst effects and create aurora displays that paint their skies in brilliant colors. The flaring activity of red dwarfs follows patterns that change over millions of years. Young red dwarfs flare more frequently and violently than their older cousins. As these stars age, their magnetic fields settle into calmer configurations, and the flares become less common. This means that planets around red dwarfs might experience hostile conditions early in their history, then settle into more stable environments as their stars mature. The transition from a flaring youth to a quiet middle age could span hundreds of millions of years, giving life time to adapt or emerge once conditions improve. The sheer abundance of red dwarf stars makes them prime targets in the search for habitable worlds. 3 out of every 4 stars in our galaxy are red dwarfs, and most of them likely host planetary systems. The nearest star to our Sun, Proxima Centauri, is a red dwarf with at least 2 confirmed planets. One of these worlds, Proxima Centauri b, orbits within its star's habitable zone and receives roughly the same amount of energy that Earth gets from the Sun. This planet completes its orbit in just 11 Earth days, racing around its dim star in the time it takes our moon to complete its phases. The discovery of thousands of red dwarf planetary systems reveals a universe where patience and persistence create the most common type of potentially habitable world. These systems operate on time scales that dwarf human comprehension, while civilizations rise and fall, while galaxies collide and merge. The red dwarfs continue their steady burn. Their planets maintain their eternal dance between day and night, creating conditions that could remain stable for longer than any other type of planetary system. In the vast cycles of cosmic time, red dwarf systems represent the universe's commitment to providing stable homes for whatever life might arise in their gentle, persistent glow. These red dwarf planetary systems create one of the most striking phenomena in the universe. When a planet orbits close enough to its star to receive the warmth needed for liquid water, something remarkable happens to its rotation. The star's gravity becomes so strong that it locks the planet's spin to match its orbit perfectly. This process, called tidal locking, means one side of the planet always faces the star, while the other side remains in eternal darkness. Imagine a world where the sun never sets on one hemisphere and never rises on the other. The day side of a tidally locked planet experiences permanent noon, with temperatures that could melt lead or boil oceans away. The night side freezes in perpetual darkness, cold enough to turn the air itself into snow. Between these two extremes lies a narrow band where temperatures might allow liquid water to exist. This twilight zone, neither fully day nor fully night, could be the most important real estate in the galaxy for life as we know it. The same gravitational forces that create our ocean tides on Earth sculpt these distant worlds on a planetary scale, just as the moon pulls our oceans back and forth, creating the rhythm of high and low tide. A red dwarf star pulls and stretches its nearby planets. Over millions of years, this constant tugging slows the planet's rotation until it matches the orbital period exactly. The moon shows us this same dance on a smaller scale. It became tidally locked to Earth long ago, which is why we always see the same face of the moon from our planet's surface. Scientists believe that most planets in the habitable zones of red dwarf stars experience this tidal locking. The habitable zone around a red dwarf sits much closer to the star than Earth's distance from the sun. This proximity makes the gravitational grip even stronger, ensuring that tidal locking happens relatively quickly in cosmic terms. A planet might become tidally locked within a few 100 million years, a brief moment compared to the billions of years. These systems can remain stable. The boundary between day and night on these worlds creates fascinating possibilities for weather and climate. Hot air from the day side rises and flows toward the cold night side, while frigid air from the dark hemisphere moves back toward the warmth. This creates a planet-wide circulation system that could transport heat around the globe. Some computer models suggest that this atmospheric circulation might make the entire planet more hospitable than initially expected. The constant wind patterns could moderate temperatures, preventing the day side from becoming too hot and keeping the night side from freezing completely. Water plays a role in these tidally locked systems. On the day side, any surface water would quickly boil away into the atmosphere. On the night side, water vapor would freeze and fall as snow or ice. But the twilight zone between these extremes might maintain liquid water in vast lakes or even shallow seas. The atmospheric circulation could carry water vapor from the day side to the night side, where it freezes and accumulates as massive ice sheets. This ice could slowly flow back toward the warmer regions, melting and creating a continuous water cycle unlike anything on Earth. The neighboring planets in these red dwarf systems often show similar patterns of tidal locking. TRAPPIST-1, a red dwarf star located 39 light-years from Earth, hosts 7 Earth-sized planets packed closely together. All of these worlds likely experience tidal locking, creating a system where each planet has its own permanent day and night sides. The planets orbit so close to each other that if you stood on one world's surface, the neighboring planets would appear larger in the sky than our moon appears from Earth. These tidal forces create more than just locked rotation. They generate internal heating within the planets themselves. As the star's gravity stretches and flexes the planet's interior, friction creates heat deep within the rocky core and mantle. This tidal heating could keep subsurface oceans liquid even on planets that seem too cold for life. Jupiter's moon Europa experiences similar tidal heating from Jupiter's massive gravity, maintaining a liquid ocean beneath its icy surface despite being far from the sun's warmth. The study of tidally locked exoplanets reveals how gravity shapes not just orbits and rotations, but entire planetary climates and the potential for life itself. These worlds represent the most common type of potentially habitable planet in our galaxy. Their extreme day-night divisions create conditions unlike anything in our solar system. Yet, they might harbor the universe's most widespread forms of life. In the eternal dance between star and planet, between heat and cold, between day and night, these tidally locked worlds demonstrate how the universe creates stability through constant motion, balance through extremes, and the possibility of life through the patient work of gravitational forces across deep time. Beyond these tidally locked worlds lie planets where the very air itself becomes a weapon against survival. On HD 189,733b, a cobalt blue giant orbiting dangerously close to its star, winds reach speeds of over 4,000 miles per hour. These aren't gentle breezes carrying the scent of distant flowers. They are screaming hurricanes of superheated gas that could circle Earth's entire equator in just 2 hours. The planet's beautiful blue color comes not from peaceful oceans, but from tiny particles of glass suspended in its atmosphere. When these glass particles get caught in those tremendous winds, they create sideways rain made of molten silicate that would shred any spacecraft in seconds. The temperature extremes on some exoplanets push the boundaries of what matter can endure. Kelt 9b orbits so close to its star that its day side reaches over 7,000 degrees Fahrenheit. This makes it hotter than many small stars themselves. The planet's atmosphere gets so scorched that molecules break apart into individual atoms. Hydrogen and helium, the simplest elements in the universe, get ripped apart and scattered into space. The planet slowly evaporates like morning dew under an impossibly intense sun, leaving behind a trail of glowing gas that stretches for millions of miles. On the opposite extreme, some planets experience cold that makes Antarctica seem tropical. Ogle 2005 BLG 390 LB sits so far from its dim red star that surface temperatures drop to nearly 400 degrees below 0 Fahrenheit. At these temperatures, carbon dioxide freezes solid and falls as snow. Any atmosphere would collapse into frozen layers, coating the ground like crystalline blankets. Yet, even in this cosmic deep freeze, the planet's core might still generate enough heat to maintain pockets of liquid water far beneath the surface, protected by miles of ice and rock. The strangest weather patterns emerge on planets with exotic atmospheric chemistry. On some worlds, it literally rains diamonds. The intense pressure and heat deep within gas giants like Neptune create conditions where carbon atoms get squeezed together until they form diamond crystals. These precious gems, some as large as hailstones, fall through layers of compressed hydrogen and helium like glittering snow in an alien winter. Scientists estimate that Neptune and Uranus might contain millions of tons of diamonds floating in their deep atmospheres, more wealth than exists in all of Earth's mines combined. Kepler 430 8b demonstrates how a planet can be simultaneously promising and terrifying. This rocky world sits squarely within its star's habitable zone, where liquid water could theoretically exist on its surface. But its star unleashes powerful flares that bombard the planet with deadly radiation every few hundred days. These stellar tantrums strip away atmosphere and sterilize any surface life that might try to take hold. The planet exists in a constant cycle of atmospheric destruction and renewal, caught between the promise of habitability and the violence of its temperamental star. Some exoplanets spin so fast they reshape themselves into cosmic eggs. Beta Pictoris B rotates once every 8 hours, much faster than any planet in our solar system. This rapid spin creates such strong centrifugal forces that the planet bulges outward at its equator and flattens at its poles. The difference between the planet's equatorial and polar diameters stretches for thousands of miles. Gravity itself gets weaker at the equator, where the surface spins away from the planet's center at tremendous speed. The most extreme exoplanet discovered so far might be PSR B1257 plus 12b, a world that orbits not a normal star, but a pulsar. Pulsars are the collapsed cores of massive stars that died in supernova explosions. They spin hundreds of times per second, while shooting beams of intense radiation across space like cosmic lighthouses. Any planet orbiting a pulsar gets bathed in radiation levels millions of times stronger than what would kill a human instantly. Yet somehow, this small rocky world survived the supernova that created its pulsar parent. It circles through space in a where physics operates at its most extreme limits, where time itself gets warped by intense gravity and magnetic fields stronger than anything else in the known universe. These extreme worlds remind us that our gentle Earth sits in a narrow band of cosmic tranquility. Between the diamond rain and glass storms, between the frozen wastelands and molten hellscapes, between the radiation-blasted surfaces and the crushing atmospheric pressures, our planet maintains the delicate conditions that allow liquid water to pool in quiet lakes and gentle rain to nourish growing forests. In the vast catalog of planetary extremes, Earth's moderation becomes its own form of cosmic miracle. The search for planets like Earth requires patience that spans decades. Scientists look for worlds that orbit their stars at just the right distance where water can exist as a liquid. Too close, and the water boils away into space. Too far, and it freezes into solid ice. This perfect zone around each star gets called the habitable zone, though astronomers sometimes call it the Goldilocks zone because the conditions need to be just right. Finding an Earth-sized planet in the habitable zone presents enormous challenges. These worlds produce no light of their own. They reflect only tiny amounts of starlight back toward our telescopes. When we search for them using the transit method, we watch for the slight dimming that happens when a planet passes in front of its star. An Earth-sized planet crossing a sun-like star blocks less than 1/100th of 1% of the star's light. That change is so small, it would be like detecting the shadow of a single grain of sand passing in front of a bright lighthouse beam from 50 miles away. The Kepler Space Telescope discovered thousands of exoplanets by watching for these tiny dips in starlight. It stared at the same patch of sky for nearly 4 years, monitoring over 150,000 stars simultaneously. The spacecraft had to remain perfectly still while making measurements precise enough to detect changes smaller than what our eyes could see if we dimmed a light bulb by removing a single photon. Kepler found that rocky planets roughly the size of Earth appear to be common throughout our galaxy. Statistical analysis of its discoveries suggests that 1 in 5 sun-like stars hosts an Earth-sized planet in its habitable zone. The closest potentially habitable exoplanet to Earth orbits Proxima Centauri, our nearest stellar neighbor, at just over 4 light years away, Proxima Centauri sits within its star's habitable zone. But this world faces unique challenges. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. The planet must orbit very close to receive enough warmth for liquid water. At that distance, the star's gravity likely locks one side of the planet in permanent daylight, while the other side remains frozen in eternal darkness. The boundary between these regions might harbor temperatures suitable for liquid water, creating a narrow ring around the planet where life could potentially survive. Red dwarf stars like Proxima Centauri live for trillions of years, far longer than larger stars like our Sun. This gives life enormous amounts of time to develop and evolve. However, young red dwarfs produce powerful flares that blast their nearby planets with intense radiation. These stellar tantrums can strip away planetary atmospheres over millions of years. Scientists debate whether planets around red dwarfs can retain enough atmosphere to support liquid water on their surfaces. The search for Earth-like worlds also focuses on the precise composition of planetary atmospheres. When exoplanets transit their stars, starlight filters through their atmospheric gases before reaching our telescopes. Different molecules absorb specific wavelengths of light, creating unique fingerprints that reveal what gases surround distant worlds. Water vapor, oxygen, methane, and carbon dioxide each leave distinct signatures in the spectrum of filtered starlight. The James Webb Space Telescope can detect these atmospheric fingerprints with unprecedented precision, allowing scientists to analyze the air of worlds hundreds of light years from Earth. Some potentially habitable planets orbit binary star systems where two stars dance around each other. These worlds experience complex seasonal patterns as they receive varying amounts of light from their dual suns. The planet Kepler-16b orbits two stars in a pattern that creates a landscape where sunsets would show two suns setting on opposite horizons, while Kepler-16b itself is too cold and gaseous to support life as we know it. Its discovery proved that stable planetary orbits can exist in binary systems. This doubles the number of star systems where Earth-like worlds might form. The definition of habitable continues to evolve as we discover the remarkable adaptability of life on Earth. Organisms thrive in environments once thought impossible for life. From the crushing depths of ocean trenches to the acidic hot springs of volcanic regions, some bacteria survive in the vacuum of space, while others live in rocks miles beneath the surface. These discoveries expand our understanding of where life might exist on distant worlds. Planets that seemed too hot, too cold, or too harsh might still harbor living organisms in protected niches beneath their surfaces or in their atmospheric clouds. Each new Earth-like planet we discover adds another piece to the growing picture of how common our world might be in the cosmic ocean. The gentle blue marble we call home may represent just one variation in a vast symphony of worlds where water flows and life might flourish under alien skies. The search for moons around distant planets began long before we had the tools to find them. Early astronomers dreamed of discovering entire solar systems orbiting other stars, complete with planets and their own families of moons. They imagined worlds like Jupiter, surrounded by dancing satellites that might harbor oceans beneath their icy shells. The challenge seemed impossible with the telescopes of the past. Even finding the planets themselves required decades of patient observation and revolutionary new techniques. Our first hints came from studying how planets move. When a large planet hosts a massive moon, the two objects actually orbit around their shared center of gravity. This creates a subtle wobble in the planet's motion that sharp-eyed astronomers can detect. Earth and our moon demonstrate this dance perfectly. They orbit around a point located about 1,700 kilometers beneath Earth's surface. From a distant star, alien astronomers would see our planet wobble slightly as it circles the sun. This same wobble signature could reveal moons around exoplanets, but the effect is incredibly small and difficult to measure across the vast distances of interstellar space. The transit method offered another path to discovery. When a planet crosses in front of its star, it blocks a tiny fraction of the star's light. If that planet has a large moon, the moon might create its own separate dimming event. Scientists realized they could search for these double-dip light curves in telescope data. The timing between the planet and moon transits would reveal the moon's orbital period and size. Kepler's Space Telescope collected millions of these light measurements, creating a treasure trove of data that researchers continue to analyze today. Computer models suggested that gas giants in other solar systems should host moon systems even more spectacular than Jupiter's 4 largest satellites. Some exoplanets orbit much closer to their stars than Jupiter does to our sun. The intense radiation and gravitational forces in these regions might strip away smaller moons while allowing massive ones to survive. Theoretical calculations indicated that super-Earth-sized moons could orbit around hot Jupiter planets. These moons would be larger than Mars, with enough gravity to hold thick atmospheres and possibly liquid water on their surfaces. The first serious candidate for an exomoon emerged from Kepler data in 2017. Kepler 1625b, a planet roughly the size of Jupiter, showed unusual variations in its transit timing and depth. The signal suggested a moon about the size of Neptune orbiting this distant world. The Discovery team used the Hubble Space Telescope to gather additional observations. They found evidence supporting their interpretation, though the signal remained at the edge of detectability. The scientific community continues to debate whether this represents a genuine moon detection or instrumental noise masquerading as a discovery. Ground-based telescopes joined the hunt using gravitational microlensing. This technique relies on the gravity of foreground objects acting like cosmic magnifying glasses. When a star with planets passes between Earth and a more distant background star, it creates a characteristic brightening pattern. Moons around the foreground planets add their own subtle signatures to this light curve. Several microlensing events have shown hints of possible moon systems, though confirming these detections requires additional observations that may never be possible. The James Webb Space Telescope opened new possibilities for exomoon detection. Its infrared vision can measure the heat signatures of planets and their potential moons. Large moons generate their own thermal emission, especially if they experience tidal heating from their host planet's gravity. Webb can also study the atmospheric compositions of transiting planets with unprecedented precision. If a planet hosts a large moon with its own atmosphere, Webb might detect the combined spectral signatures of both worlds during transit events. Radio telescopes offer yet another detection method. Jupiter's moon Io generates powerful radio emissions through its interactions with Jupiter's magnetic field. Similar radio signals might emanate from exomoons orbiting magnetized gas giants. The Square Kilometer Array, currently under construction, will have the sensitivity to detect these faint radio whispers from nearby star systems. These observations could reveal not just the presence of moons, but also details about their compositions and magnetic environments. The discovery of the first confirmed exomoon will mark a new chapter in our understanding of planetary systems. Moons provide additional environments where life might develop, effectively doubling or tripling the number of potentially habitable worlds in each system. Large moons can stabilize their planet's rotation, moderate climate variations, and create tidal forces that might be essential for the emergence of complex life. The patient search continues across multiple wavelengths of light, waiting for that first unmistakable signal from a world orbiting another world in the depths of space. The habitable zone around a star was once thought to be fixed, like a painted ring in space. Scientists believed this zone stayed the same distance from its star throughout the system's lifetime. This simple picture has crumbled under the weight of new discoveries. The habitable zone breathes and shifts like a living thing, expanding and contracting as its star ages and changes. Young stars burn much dimmer than their older selves. The sun produced only 70% of its current energy when Earth first formed 4.5 billion years ago. This means Earth sat outside the habitable zone during its earliest years, too cold for liquid water to exist on its surface. Yet geological evidence shows that oceans existed on early Earth. This puzzle, called the faint young sun paradox, suggests that other factors beyond stellar energy determine where life can thrive. The atmosphere acts as a cosmic thermostat, trapping heat through greenhouse gases. Early Earth's thick atmosphere of carbon dioxide and methane kept the planet warm enough for liquid water, even with a dimmer sun. As the sun gradually brightened over billions of years, Earth's atmosphere thinned through natural processes, maintaining temperatures suitable for life. This delicate balance shows how planets can stay habitable even as their star's habitable zone shifts outward. Mars tells a different story of habitable zone evolution. The red planet sits near the outer edge of our sun's current habitable zone, too cold for liquid water on its surface today. But Mars once had a thicker atmosphere and flowing rivers. As the sun brightened and Mars lost most of its atmosphere to space, the planet fell out of the habitable zone's sweet spot. The shifting boundaries left Mars as a frozen desert, its ancient riverbeds now filled only with dust and memory. Some planets experience dramatic habitable zone changes during their star's death throes. When a star like the Sun exhausts its nuclear fuel, it swells into a red giant, becoming hundreds of times brighter. This expansion pushes the habitable zone far outward, beyond the orbits of Jupiter and Saturn. Moons of these gas giants, previously frozen solid, might suddenly find themselves bathed in gentle warmth. Europa and Enceladus, now icy worlds orbiting Jupiter and Saturn, could become tropical paradises when the Sun enters its red giant phase in 5 billion years. The discovery of planets around red dwarf stars has revealed another surprise about habitable zones. Red dwarfs burn so slowly that they remain stable for trillions of years, far longer than the current age of the universe. Their habitable zones sit very close to the star, where planets complete their orbits in just days or weeks. These nearby worlds receive intense stellar radiation and powerful magnetic fields that can strip away their atmospheres. Yet, some red dwarf planets might maintain thick atmospheres through volcanic outgassing, keeping their habitable zones active despite the harsh conditions. Binary star systems create habitable zones that dance and weave through space. When two stars orbit each other, their combined energy output changes as they move closer together and farther apart. Planets in these systems experience seasons that last for decades or centuries, as their habitable zone expands and contracts with the stars' orbital dance. Some binary systems have stable habitable zones that persist between the two stars, creating figure-eight patterns where life might adapt to the complex rhythms of dual sunrises and sunsets. Scientists have discovered that planets can carry their own habitable zones through space. Rogue planets, ejected from their birth systems, drift through the galaxy without any star to warm them. These wandering worlds might maintain liquid water oceans beneath thick ice shells, heated by radioactive decay in their cores and tidal forces from large moons. The habitable zone becomes a bubble around the planet itself, independent of any star's energy. The James Webb Space Telescope has begun detecting water vapor in the atmospheres of planets that orbit well outside their star's traditional habitable zone. These distant worlds receive energy from tidal heating as their elliptical orbits stretch and compress the planet's interior. The friction from this constant flexing generates enough heat to maintain liquid water, creating habitable conditions in unexpected places. Even the definition of habitability continues to evolve. Life on Earth thrives in environments once thought impossible, from boiling hot springs to the frozen depths of Antarctica. These discoveries expand the boundaries of where scientists search for habitable worlds. The habitable zone now includes any region where liquid water might exist, whether on a planet's surface, in subsurface oceans, or in atmospheric clouds high above the ground. The shifting nature of habitable zones means that life might be far more common than early estimates suggested. Planets can enter and exit habitable conditions multiple times during their history, giving life many chances to emerge and evolve. The universe becomes a vast garden where the seasons of habitability bloom and fade across billions of years, each cycle offering new opportunities for the spark of life to ignite. Water connects every system in the universe through an elegant dance of chemistry and physics. This simple molecule of two hydrogen atoms bonded to one oxygen atom becomes the foundation for life as we know it. On distant exoplanets, water vapor rises from warm oceans and falls as rain, just as it does on Earth. The same physical laws that govern our weather systems operate on worlds thousands of light years away. When astronomers detect water in an exoplanet's atmosphere, they glimpse the same processes that have shaped our home for billions of years. The presence of water on an exoplanet depends on a delicate balance between stellar radiation and atmospheric pressure. Too much heat from a nearby star, and water boils away into space. Too little warmth, and it freezes into solid ice that cannot support liquid-based life. The sweet spot where water remains liquid creates a zone of possibility around every star. This habitable zone shifts and changes as stars age and evolve. Young stars burn brighter and push their habitable zones farther out. Older stars dim and pull these zones closer in. Planets that start frozen can warm up as their star matures. Worlds that begin with flowing oceans might eventually freeze as their star cools down. The magnetic field of a planet plays a role in protecting its water from the harsh radiation of space. Earth's magnetic field acts like an invisible shield, deflecting charged particles from the solar wind that would otherwise strip away our atmosphere. Mars lost much of its water because its magnetic field weakened billions of years ago. The solar wind gradually eroded the Martian atmosphere, allowing precious water molecules to escape into the void. Exoplanets with strong magnetic fields can hold onto their water for billions of years. Those without this protection might lose their oceans within a few 100 million years. The composition of a planet's atmosphere determines whether water can exist as a liquid on the surface. Carbon dioxide creates a greenhouse effect that traps heat from the star. Venus has too much carbon dioxide, creating a runaway greenhouse that boiled away all its water long ago. The surface temperature on Venus reaches 900 degrees Fahrenheit, hot enough to melt lead. Mars has too little atmosphere to trap sufficient heat, so water freezes at the poles and underground. Earth sits in the perfect middle ground where atmospheric pressure allows water to exist in all three states. Ice caps store water at the poles. Liquid oceans cover most of the surface. Water vapor in the atmosphere creates clouds that regulate temperature. The distance between a planet and its star creates the foundation for water's existence. But other factors fine-tune the conditions. The tilt of a planet's axis determines how evenly heat spreads across the surface. Earth's 23-degree tilt creates seasons that help distribute solar energy from the equator to the poles. A planet with no tilt would have permanent ice caps and scorching equatorial regions. Too much tilt would create extreme seasons that freeze and bake the surface in endless cycles. The rotation speed of a planet affects how heat moves through the atmosphere. Fast-spinning worlds mix their air efficiently, creating moderate temperatures. Slowly rotating planets develop extreme hot and cold regions that make water difficult to maintain. Volcanic activity connects the interior of a planet to its surface water through the carbon cycle. Volcanoes release carbon dioxide that was trapped in rocks deep underground. This carbon dioxide enters the atmosphere and affects the planet's temperature. Rain washes carbon dioxide out of the air and carries it to the oceans. Marine organisms use this carbon to build shells and skeletons. When these creatures die, their remains sink to the ocean floor and eventually get recycled back into the planet's interior through plate tectonics. This carbon cycle regulates the amount of greenhouse gas in the atmosphere over millions of years. Planets without volcanic activity cannot recycle their carbon and might lose the ability to maintain liquid water. The gravitational pull of nearby planets and moons affects the shape of a world's orbit around its star. Circular orbits provide steady amounts of heat throughout the year. Elliptical orbits create seasons of warmth and cold that can freeze and thaw surface water. Jupiter's gravity has shaped the orbits of many planets in our solar system, keeping Earth in a stable circular path that maintains consistent temperatures. On exoplanets, giant planets can either stabilize smaller worlds or throw them into chaotic orbits that make water impossible to maintain. The dance of gravity between multiple planets creates the rhythm that determines whether water can flow on distant shores. Each world's story of water connects to every other object in its solar system through these invisible threads of gravitational influence. The sky above an alien world tells the story of its atmosphere through color. On Earth, our sky appears blue because tiny molecules in the air scatter blue light more than other colors. This same process creates different colored skies on distant planets, depending on what gases float in their atmospheres. A planet with a thick methane atmosphere might glow orange or red during the day. Worlds wrapped in dense carbon dioxide could shine with pale yellow or amber light filtering down to their surfaces. The star that lights each planet also paints its sky with unique hues. Red dwarf stars, the most common type in our galaxy, cast everything in deep crimson tones. Planets orbiting these cool stars would see perpetual sunset colors, even at midday. The plants on such worlds might appear black or deep purple instead of green, absorbing the red light more efficiently than Earth's vegetation captures our sun's yellow glow. Blue giant stars flood their planets with intense ultraviolet radiation, creating skies that shimmer with electric blues and violets that would blind human eyes. Dust storms can transform planetary skies from season to season. Mars shows us this change in our own solar system, where massive dust storms turn the normally butterscotch sky into a dark orange haze that can last for months. On some exoplanets, silicon dust creates skies that sparkle like glitter as microscopic glass particles catch and reflect starlight. Iron particles in the atmosphere of hot Jupiter planets create skies that shift from deep red to metallic gray as the planet rotates and different layers of atmosphere face the star. Water vapor changes the color of alien skies just as it does on Earth. Planets with thick, water-rich atmospheres might display brilliant white or silver skies as sunlight bounces off countless tiny droplets suspended in the air. These worlds could experience rainbow effects far more dramatic than anything we see on Earth. With multiple arcs of color spanning their entire sky dome, the amount of water vapor in an atmosphere changes over thousands of years as planets warm and cool, creating slow shifts in sky color that mark the passage of geological ages. Volcanic activity adds temporary splashes of color to planetary skies. When volcanoes erupt, they inject sulfur compounds high into the atmosphere, creating yellow and green tints that can persist for decades. Some exoplanets experience constant volcanic activity due to gravitational stress from nearby massive planets. These tortured worlds might display permanent aurora-like glows as charged particles from their star interact with volcanic gases streaming into space. The thickness of an atmosphere determines how much starlight reaches a planet's surface and what colors survive the journey downward. Thin atmospheres allow most colors through, creating skies similar to the black of space, but tinted by whatever gases are present. Thick atmospheres filter out certain colors completely, leaving only specific wavelengths to illuminate the surface. Venus shows this effect in our solar system, where the incredibly dense carbon dioxide atmosphere creates an orange greenhouse that traps heat and blocks most sunlight from reaching the ground. Binary star systems create the most spectacular sky shows in the galaxy. Planets orbiting two stars experience double sunrises and double sunsets, with each star contributing its own color to the atmospheric display. A world circling a red dwarf and a white dwarf might see pink dawns followed by blue-white afternoons, then purple twilights as the two stars set at different times. The gravitational dance between binary stars slowly changes over millions of years, altering the planet's orbit and creating gradual shifts in how much light each star contributes to the sky's color palette. Seasonal changes on tilted planets create annual cycles of sky color transformation. As different hemispheres lean toward or away from their star, atmospheric circulation patterns shift and carry different types of particles to various altitudes. What appears as a blue morning sky in summer might become deep purple in winter as dust and ice crystals redistribute through the changing air currents. The age of a planet's atmosphere also influences its color over cosmic time. Young atmospheres often contain more hydrogen and helium left over from planetary formation, creating pale, washed-out skies. As these light gases escape to space and heavier molecules accumulate from volcanic outgassing and comet impacts, the sky's color deepens and becomes more vivid. Ancient planets with stable atmospheres might maintain the same sky color for billions of years, while younger worlds experience dramatic color shifts as their atmospheric composition evolves. Each alien sunset represents a moment in a planet's long journey through time, painting temporary masterpieces across skies that have been changing color since the first stars began to shine. The most spectacular light shows in the universe happen around binary star systems, where two stars orbit each other in an eternal cosmic dance. These stellar pairs create planets that experience sunrises and sunsets, unlike anything we could imagine from Earth. When a planet orbits both stars in a binary system, called a circumbinary planet, it receives light from two different colored suns that paint the sky in constantly shifting hues throughout each day. Kepler 16b became the first confirmed planet orbiting two stars, much like the fictional Tatooine from Star Wars. This gas giant receives orange light from one star and red light from its smaller companion. During the planet's day, the sky shifts from deep amber when both stars shine overhead to brilliant copper, when only the larger star illuminates the atmosphere. The smaller red dwarf star casts everything in crimson shadows that dance across the planet's cloud tops like aurora light frozen in time. The gravitational pull between binary stars creates complex orbital patterns that cause dramatic changes in how much light reaches their planets. Sometimes both stars align on the same side of the planet, flooding it with intense double starlight that turns the atmosphere into a blazing furnace of white and gold. Other times, the stars position themselves on opposite sides of the planet, creating a twilight world where orange dawn meets red sunset simultaneously across the same sky. Binary star systems produce planets with seasons that follow no earthly pattern. as the two stars orbit each other, their combined gravitational influence changes the planet's distance from the stellar pair. These orbital variations create temperature swings that can shift a world from frozen ice to boiling steam within a single planetary year. The changing distance also affects how the atmosphere scatters light, causing the sky to cycle through deep blues during cold periods and pale yellows during warmer phases. Some binary planets experience double eclipses when one star passes behind the other as viewed from the planet's surface. During these events, the sky transforms from bright daylight to an eerie twilight, illuminated only by the corona of the hidden star. The remaining visible star appears surrounded by a shimmering halo of light that creates rainbow patterns across the planet's atmosphere. These double eclipses can last for hours, painting the world in ghostly silver light that makes ice crystals sparkle like scattered diamonds. The most extreme binary systems contain a white dwarf star paired with a normal star. The white dwarf's intense ultraviolet radiation strips material from its companion, creating streams of glowing gas that spiral between the two stars. Planets in these systems receive not just visible light, but powerful bursts of X-rays and ultraviolet energy that ionize their atmospheres. The result is a world where the sky glows with permanent aurora, displays that shift from green to purple to brilliant white as charged particles cascade through the upper atmosphere. Contact binary systems push the boundaries of planetary illumination even further. These stellar pairs orbit so close together that they actually touch, sharing material in a bridge of superheated gas. The combined light from these merged stars creates planets bathed in constant, intense radiation that turns their atmospheres into glowing plasma. Any solid surface would melt under this stellar furnace, but the light show would be magnificent. The sky would burn with colors that have no names, shifting from electric blue to blazing magenta as the merged stars pulse with unstable energy. Binary star planets also experience unique shadow effects that create patterns impossible in single star systems. When both stars shine from different angles, objects cast double shadows in complementary colors, A mountain might throw an orange shadow from one star and a red shadow from the other, creating zones where the shadows overlap in deep purple darkness. These shadow patterns shift throughout the day as the stars move across the sky, painting the landscape in an ever-changing mosaic of colored light and darkness. The search for habitable planets around binary stars focuses on finding worlds where the complex light patterns might still allow liquid water to exist. Scientists have discovered that some binary planets maintain stable temperatures despite receiving light from two stars. The key lies in finding the right orbital distance where the combined stellar radiation provides steady warmth without creating extreme temperature swings that would boil away any oceans. Each binary star system creates its own unique signature of light that astronomers can detect from thousands of light years away. The combined spectrum from two different colored stars produces distinctive patterns that reveal not just the presence of planets, but also clues about their atmospheric composition. When a planet passes in front of both stars during its orbit, it creates a complex light curve that tells the story of a world dancing between two suns, forever bathed in the shifting colors of its binary stellar companions. In the quiet depths of space, young planetary systems hum with the deep vibrations of creation. When NASA's instruments detect these cosmic sounds, they reveal the gentle rumble of worlds still taking shape. The Spitzer Space Telescope has recorded the low-frequency vibrations that emerge from protoplanetary disks, those spinning clouds of dust and gas where new planets slowly gather mass. These vibrations translate into sounds that resemble distant thunder, the deep bass notes of cosmic construction happening over millions of years. The process begins with the softest whisper. Tiny dust, grains no bigger than smoke particles, drift through the disk, occasionally bumping into each other with impacts so gentle they would be silent to human ears. But sensitive instruments can detect the collective motion of trillions of these encounters, creating a subtle hiss like sand shifting in a gentle breeze. As these grains stick together, they form larger clumps that produce slightly deeper tones when they collide and merge. Within these stellar nurseries, the temperature variations create their own acoustic signatures. Hot regions near the young star expand and cool in cycles, generating pressure waves that ripple outward through the disk. These waves carry the rhythm of stellar heating, a steady pulse that sounds like a distant heartbeat. When converted to audio frequencies humans can hear, the Kepler Space Telescope detected similar pulsations in hundreds of young star systems, each one beating with its own unique tempo as planets slowly coalesce from the surrounding material. As planetary embryos grow larger, their gravitational influence begins to clear gaps in the disk around them. This process creates distinctive sound patterns that astronomers call gap music. The forming planet acts like a cosmic vacuum cleaner, sweeping up material in its orbital path and creating empty lanes in the disk. When other particles encounter these gaps, they produce echoing sounds that bounce back and forth across the cleared space. Radio telescopes have captured these echoes from systems like H.L. Tauri, where multiple planets are carving concentric rings through the dusty disk. The most dramatic sounds come from the violent collisions that shape young worlds. When two planetary embryos crash into each other, the impact generates seismic waves that ring through the growing planet like a struck bell. These collision sounds can persist for thousands of years as the merged world slowly settles into its new shape. Computer simulations suggest that Earth itself once rang like a bell for centuries after the giant impact that formed our moon. The deep, resonant tones would have been felt rather than heard, vibrating through the molten rock of our young planet. Young gas giant planets create their own unique acoustic fingerprints as they rapidly accumulate atmosphere from the surrounding disk. The process sounds like a cosmic waterfall, a continuous rushing noise as gas streams onto the growing world. Jupiter-sized planets can double their mass in just a few thousand years during this phase, creating gravitational disturbances that generate powerful sound waves throughout their stellar system. These waves carry information about the planet's growth rate and final size, encoded in frequencies that vary with each world's unique formation story. the magnetic fields of young planets also contribute to the cosmic symphony. As these worlds develop their magnetic shields, they begin to interact with the charged particles streaming from their parent star. This interaction creates radio emissions that sound like ethereal whistles and chirps when played through speakers. The Cassini spacecraft recorded similar sounds from Saturn's magnetosphere, haunting melodies that rise and fall as the planet rotates, and its magnetic field sweeps through space. Perhaps the most remarkable discovery is that some young planets appear to sing in harmony with their forming moons. The gravitational dance between a growing planet and its satellite creates tidal forces that generate rhythmic vibrations in both bodies. These paired oscillations produce chord-like combinations of frequencies that suggest even the earliest stages of planetary formation follow musical principles of resonance and harmony. The dust itself carries sound in ways that surprise scientists. Individual grains spinning through space create tiny electromagnetic pulses as they tumble end over end. Billions of these spinning particles generate a collective hum that permeates young stellar systems. This cosmic static provides a constant background rhythm against which the louder sounds of planetary formation play out their ancient melodies. Radio telescopes continue to detect these formation sounds from stellar nurseries throughout our galaxy. Each young system contributes its own voice to a vast chorus of worlds being born. The Atacama Large Millimeter Array has recorded the acoustic signatures of planet formation in systems hundreds of light years away, revealing that the process of building worlds creates remarkably similar sound patterns regardless of where in the galaxy it occurs. These cosmic construction sites remind us that even in the apparent silence of space, the universe resonates with the deep music of creation itself. The oldest known planet in our galaxy carries the elegant designation PSR-B 16-2026b, though astronomers often call it simply Methuselah. This ancient world formed 12.7 billion years ago, when our universe was barely 1 billion years old. The numbers tell a story of cosmic patience. While Earth celebrated its 4.5 billionth birthday, Methuselah had already witnessed the birth and death of countless stellar generations across nearly 13 billion years of existence. The mathematics of this ancient planet's discovery required extraordinary precision. Methuselah orbits not one star, but two stellar remnants locked in their own gravitational dance. A pulsar spins 30 times per second, sending radio beams sweeping across space like a cosmic lighthouse. Its companion white dwarf completes one orbit around the pulsar every 6 months and 12 days. The planet itself traces a much larger circle, taking 100 years to complete a single journey around both stars. Scientists detected Methuselah by measuring tiny changes in the pulsar's radio signals. The spinning neutron star keeps time more accurately than any atomic clock on Earth. When the planet's gravity tugs the pulsar slightly closer or farther from us, the radio pulses arrive a few millionths of a second early or late. These microscopic timing variations revealed the presence of a world 2.5 times more massive than Jupiter, orbiting at a distance roughly twice that between our Sun and Pluto. The age calculation relies on stellar evolution models that trace the life cycles of stars with mathematical precision. The white dwarf companion began as a star 8 times more massive than our Sun. Such stars burn through their nuclear fuel in approximately 40 million years before swelling into red giants and then collapsing into white dwarf remnants. The pulsar formed when an even more massive star exploded as a supernova, leaving behind a neutron star spinning at incredible speed. For a planet to survive both stellar deaths requires extraordinary orbital mechanics. Computer simulations show that Methuselah must have originally orbited much farther from the binary pair, as the first star evolved into a red giant. Its outer layers expanded to nearly 100 times its original size. The planet's orbit gradually spiraled inward due to drag from the tenuous stellar atmosphere, but remained far enough away to avoid being consumed entirely. When the second star exploded as a supernova, the blast should have stripped away any remaining planetary atmosphere and possibly ejected the world from the system entirely. The fact that Methuselah survived both catastrophes speaks to the delicate balance of gravitational forces and orbital distances. The planet's current orbit represents a stable solution to a three-body problem involving two stellar remnants and a massive world. The discovery of such an ancient planet challenges our understanding of early planetary formation. 12.7 billion years ago, the universe contained far fewer heavy elements than today. The first generation of stars consisted almost entirely of hydrogen and helium. Only after these massive stars lived their brief lives and died in supernova explosions did they scatter carbon, oxygen, silicon, and iron into space. Planets like Earth require these heavier elements to form solid surfaces and rocky cores. Yet Methuselah formed when the universe contained less than 1% of the heavy elements present today. This suggests that gas giant planets can assemble from primarily hydrogen and helium, requiring only tiny amounts of heavier materials to serve as condensation nuclei. The mathematics of planetary accretion indicate that even trace amounts of dust and ice can trigger the runaway growth of massive atmospheric envelopes around small solid cores. The orbital period ratios in the Methuselah system display the same mathematical harmonies found throughout the cosmos. The pulsar's 30 millisecond rotation period, the binary orbit of 6 months, and the planet's century-long year create a nested hierarchy of timescales. Each larger cycle contains thousands or millions of smaller ones, like Russian dolls of orbital motion, stretching across vastly different scales of space and time. Radio observations reveal that the pulsar's magnetic field creates a protective bubble around the entire system. Charged particles streaming from the spinning neutron star generate a magnetosphere extending well beyond the planet's orbit. This invisible shield deflects most of the high-energy cosmic rays that would otherwise bombard Methuselah's surface. The mathematical relationship between the pulsar's rotation rate, magnetic field strength, and particle density creates a stable radiation environment that has persisted for billions of years. Temperature calculations show that Methuselah receives virtually no heat from its stellar companions. The white dwarf has cooled to less than 5,000 degrees, while the pulsar emits only faint radio waves and X-rays. The planet's surface temperature hovers near absolute zero, creating conditions where hydrogen and helium would freeze solid. Any atmosphere that survived the supernova explosion has long since condensed into ice, covering the world's surface like a crystalline shroud. When starlight passes through a distant planet's atmosphere, it carries the chemical fingerprints of that alien world back to Earth. Each gas molecule absorbs specific colors of light, creating dark lines in the spectrum like a cosmic barcode. Scientists can read these patterns to determine what elements float in atmospheres trillions of miles away. Water vapor absorbs infrared light at precise wavelengths. Methane creates its own unique signature. Carbon dioxide leaves unmistakable marks across multiple parts of the spectrum. The Hubble Space Telescope first detected water vapor in an exoplanet's atmosphere in 2013. Analyzing light from a world called HD 209,458b. As the planet crossed in front of its star, starlight filtered through the thin edge of its atmosphere before reaching Earth. The water molecules absorbed specific infrared wavelengths, revealing their presence in that distant sky. This technique, called transmission spectroscopy, transforms every planetary transit into a chemical analysis of alien air. Sodium creates a distinctive yellow glow when heated, the same color that gives street lamps their warm light. Astronomers have detected sodium in the atmospheres of dozens of hot gas giants, where temperatures reach thousands of degrees. The intense heat strips electrons from sodium atoms, causing them to emit their characteristic yellow signature. Some exoplanets show such strong sodium absorption that their atmospheres appear to glow with this golden hue when viewed through powerful telescopes. The James Webb Space Telescope can detect carbon dioxide, water vapor, methane, and dozens of other molecules in exoplanet atmospheres with unprecedented precision. Its infrared vision penetrates cosmic dust and captures the faint heat signatures of distant worlds. recent observations revealed clouds of silicate particles in the atmosphere of WASP 96b. Tiny grains of rock and metal suspended in alien skies like microscopic sand dunes floating through space. Earth's atmosphere creates a paper-thin shell around our planet, extending only about 60 miles above the surface. If Earth were the size of an apple, our entire breathable atmosphere would be thinner than the apple's skin. This delicate layer contains the precise mixture of gases that allows liquid water to exist and life to flourish. Nitrogen makes up 78% of our air, providing a stable background gas that doesn't react easily with other elements. Oxygen comprises 21%, the perfect concentration to support complex life without making everything burst into flames. The remaining 1% of Earth's atmosphere includes argon, carbon dioxide, and trace amounts of other gases that play roles in maintaining our planet's climate. Carbon dioxide traps just enough heat to keep Earth warm, but not so much that our oceans boil away like they did on Venus. Water vapor acts as both a greenhouse gas and a cooling agent, forming clouds that reflect sunlight back to space, while also trapping heat near the surface. Mars lost most of its atmosphere to space over billions of years because its weak magnetic field couldn't protect the thin air from solar wind. The red planet's atmospheric pressure is less than 1% of Earth's, too thin to keep liquid water stable on the surface. Any water that appears quickly boils away or freezes solid, depending on the temperature. Scientists have detected methane in Mars's thin atmosphere, a gas that breaks down quickly under ultraviolet light and must be constantly replenished by some unknown source. Venus trapped too much heat in its thick atmosphere, creating a runaway greenhouse effect that turned the planet into a hellish world where lead would melt. The surface temperature reaches 900 degrees Fahrenheit, hot enough to glow like the heating element in a toaster. Sulfuric acid clouds float 30 miles above the surface, raining corrosive droplets that never reach the ground because they evaporate in the intense heat. The habitable zone around each star represents a narrow band where liquid water can exist on a planet's surface, too close to the star, and water boils away into space. Too far away, and it freezes into ice. Earth orbits in the perfect spot within our sun's habitable zone, receiving just the right amount of energy to maintain temperatures, where water flows as a liquid across most of the planet's surface. Red dwarf stars have habitable zones much closer to the star because these small suns burn cooler and dimmer than our sun. A planet in the habitable zone around a red dwarf might orbit its star in just a few weeks, staying warm through tidal heating as gravitational forces stretch and squeeze the world's interior. The constant flexing generates heat that could keep subsurface oceans liquid even on worlds that seem too cold for life. Atmospheric escape continues to shape every world in the universe. Light gases like hydrogen and helium drift away from planets over geological time, while heavier molecules like carbon dioxide and water vapor tend to stay bound by gravity. The balance between atmospheric loss and replenishment determines whether a planet can maintain the stable conditions necessary for liquid water and potentially life itself. Some planets exist in places where our models say they simply cannot form. HD 106906b orbits its star at a distance 20 times farther than Pluto orbits our sun. This massive world, 11 times heavier than Jupiter, sits so far from its parent star that it receives almost no heat or light. Current theories of planet formation cannot explain how such a giant world could assemble at such an enormous distance from its star. The disk of dust and gas that builds planets should be too thin and cold at that distance to gather enough material for such a massive world. Scientists discovered planets orbiting pulsars, the rapidly spinning remnants of exploded stars. These neutron stars emit deadly radiation and spin hundreds of times per second, creating an environment more hostile than the surface of the sun. Yet somehow, planets formed around these cosmic lighthouses. The first confirmed exoplanets ever discovered orbit the pulsar PSR b 1257 plus 12, worlds that endure constant bombardment from high-energy particles. These planets might be the cores of gas giants that survived their star's violent death, stripped of their atmospheres, but still held in orbit by the pulsar's immense gravity. WASP 17b spins backward compared to its star's rotation, a phenomenon that challenges our understanding of how planetary systems form. Most planets should rotate in the same direction as their star because they all formed from the same spinning disk of material. This hot Jupiter somehow ended up with retrograde rotation, possibly after a violent encounter with another planet that flipped its orbit completely around. The planet's atmosphere has been inflated to twice the size of Jupiter despite having only half the mass, creating a world so puffy that it would float in water if you could find an ocean large enough. Kepler 78b orbits so close to its star that its year lasts just 8.5 hours. This rocky planet, similar in size to Earth, races around its sun at a distance closer than Mercury gets to our sun. The planet's surface temperature reaches over 3,600 degrees Fahrenheit, hot enough to melt iron. Current models of planet formation suggest that rocky worlds cannot form so close to their stars because the intense heat would prevent solid materials from condensing. Yet Kepler 78b exists, forcing scientists to reconsider how planets can migrate inward after forming in cooler regions. Some planets orbit their stars in highly stretched elliptical paths that carry them from scorching heat to freezing cold during each orbit. HD 80,606b follows such an extreme oval orbit that it swings from a distance similar to Earth's orbit all the way in closer than Mercury in just 111 days. During its closest approach, the planet's temperature soars by over 1,000 degrees in just 6 hours. These eccentric orbits might result from gravitational interactions with other planets or passing stars that stretched the originally circular paths into elongated ovals. Scientists have found planets made almost entirely of carbon, worlds where diamond rain might fall from graphite clouds. These carbon planets form in regions of space where carbon outnumbers oxygen, creating conditions completely unlike those that built our rocky worlds. instead of silicate rocks and metal cores. These planets might have surfaces of pure diamond, with atmospheres of carbon monoxide and methane. The extreme pressure deep inside these worlds could compress carbon into forms of diamond harder than any material found on Earth. TOI 849b represents another puzzle in planetary science. This world appears to be the exposed core of a gas giant that somehow lost its entire atmosphere. The planet orbits so close to its star that any gas envelope should have been stripped away long ago, leaving behind only the solid core. But cores this massive should be able to hold onto at least some atmosphere through their own gravity. The planet's existence suggests that gas giants can lose their atmospheres through processes we do not yet fully understand. Planets continue to surprise us by existing in binary star systems where gravitational forces should tear them apart. Kepler 47 hosts at least 3 planets orbiting both stars in a complex dance of gravity. These circumbinary planets must navigate the changing gravitational fields of 2 stars while maintaining stable orbits for millions of years. The discovery of such worlds expands the possible locations where planets might form and survive. Each impossible planet teaches us that the universe operates by rules more complex and flexible than our current theories suggest. These worlds push the boundaries of what we thought possible, revealing that planet formation can occur under conditions far more extreme and varied than we ever imagined. The cosmos continues to create worlds in ways that challenge our deepest assumptions about how planetary systems come to be. The closest star to our Sun holds a planet that might become humanity's first destination beyond our solar system. Proxima Centauri, a red dwarf star just over 4 light-years away, hosts a world called Proxima Centauri. B. This planet sits within its star's habitable zone, where liquid water could exist on its surface. The world receives slightly more energy from its star than Earth gets from the Sun, making it one of the most promising candidates for future exploration. Proxima b completes its orbit in just 11 Earth days, racing around its small, dim star at a distance closer than Mercury orbits our Sun. The Alpha Centauri system contains 3 stars locked in a gravitational dance that will continue for billions of years. Alpha Centauri A and B orbit each other every 80 years, while tiny Proxima Centauri circles the pair at a much greater distance. This triple star system represents our closest stellar neighbors, and recent discoveries suggest it may host multiple planets. Alpha Centauri closely resembles our Sun in size and temperature, making any planets around it particularly interesting targets for future study. The system's proximity means that light from these stars left them just 4 years ago, creating an almost real-time window into another corner of the galaxy. Barnard's star, the second closest star system to Earth, harbors a super-Earth that orbits beyond its star's habitable zone. This world, called Barnard B, takes about 233 Earth days to complete one orbit around its red dwarf host. The planet likely experiences surface temperatures similar to Jupiter's moon Europa, suggesting that any water would remain frozen. Barnard's star moves across our sky faster than any other known star, racing through space at over 100 kilometers per second relative to the Sun. This rapid motion will bring the star slightly closer to Earth over the next 10,000 years before it begins moving away again. Wolf 359, located just under 8 light-years from Earth, recently revealed 2 planets orbiting within its system. Both worlds orbit closer to their star than Mercury orbits the Sun, completing their years in just a few Earth days. The inner planet, Wolf 359b, receives intense radiation from its red dwarf host, making its surface likely too hot for liquid water. These nearby planetary systems give us glimpses of how common planets might be around the small, long-lived red dwarf stars that make up most of our galaxy's stellar population. The future of these close stellar neighbors unfolds across timescales that dwarf human history. Red dwarf stars like Proxima Centauri will continue burning for trillions of years, long after our Sun has expanded into a red giant, and then faded to a white dwarf. The planets orbiting these nearby stars will witness the death and birth of countless stellar generations throughout the Milky Way, Proxima b will experience the gradual brightening of its host star as nuclear fusion slowly changes the star's internal structure over billions of years. Gravitational interactions between the Alpha Centauri stars will continue their complex orbital dance, occasionally bringing the stars closer together or pushing them farther apart. These changes will subtly alter the amount of starlight reaching any planets in the system, creating long-term climate cycles that span millions of years. The planets themselves will continue their steady orbits, their surfaces shaped by the patient work of geological processes and the gentle pressure of stellar winds. Over cosmic time, the motion of stars through the galaxy will reshape our local stellar neighborhood. Barnard's star will eventually pass close enough to our solar system to become the nearest star to Earth. Though this encounter lies tens of thousands of years in the future, other stars will drift into our cosmic vicinity, while current neighbors slowly recede into the distance. The planets around these wandering stars will travel with them, carrying their stories across the galaxy like messages in bottles floating through an ocean of space. New planets may still be forming around these nearby stars, condensing from disks of dust and gas that we have not yet detected. Young planets will grow through the slow accumulation of cosmic debris, their surfaces bombarded by asteroids and comets that deliver water and organic compounds. Some of these future worlds might develop the precise conditions needed for life to emerge and flourish. The search for life around our nearest stellar neighbors represents one of humanity's greatest future challenges. Advanced telescopes will study the atmospheres of these nearby worlds, searching for the chemical signatures that might indicate biological processes. The planets orbiting Proxima Centauri, Alpha Centauri, and other close stars offer our best hope of detecting life beyond Earth within the next century. These worlds, separated from us by just a few years of light travel, hold the keys to answering whether life represents a common phenomenon throughout the universe or remains a rare and precious occurrence in the cosmic dark. The search for life extends far beyond the rocky planets that orbit within their star's warm embrace. Hidden beneath thick shells of ice, ocean worlds drift through the cold outer regions of solar systems, harboring vast seas that never see sunlight. These frozen moons contain more liquid water than all of Earth's oceans combined, creating environments where life might thrive in eternal darkness. Europa, Jupiter's fourth largest moon, hides an ocean beneath its icy crust that stretches twice as deep as Earth's deepest trenches. The gravitational pull of massive Jupiter flexes Europa's rocky core, generating heat through friction that keeps this buried ocean from freezing solid. Enceladus, a small moon of Saturn, shoots towering geysers of water vapor and ice particles from cracks near its south pole. These dramatic plumes reach heights of 500 miles above the moon's surface, creating a thin atmosphere and feeding Saturn's outermost ring with fresh ice crystals. Scientists have detected organic compounds and minerals in these geysers, suggesting that Enceladus harbors a warm ocean beneath its frozen shell. The moon's interior ocean likely makes contact with its rocky seafloor, creating conditions similar to Earth's deep-sea hydrothermal vents, where life first emerged billions of years ago. Titan, Saturn's largest moon, presents an even more complex water story. Beneath its thick atmosphere of nitrogen and methane lies a subsurface ocean of liquid water mixed with ammonia, creating a natural antifreeze that prevents the ocean from solidifying. This hidden sea may contain more water than all of Earth's surface oceans, lakes, and rivers. Titan's surface features lakes and rivers of liquid methane and ethane, making it the only world besides Earth known to have stable liquid on its surface. The interaction between Titan's surface chemistry and its buried ocean creates a layered system where different types of life might exist at different depths. Ganymede, Jupiter's largest moon and the biggest moon in our solar system, also conceals a saltwater ocean beneath multiple layers of ice. This moon generates its own magnetic field, the only moon known to do this, which helps protect its subsurface ocean from Jupiter's intense radiation. The magnetic field creates auroras at Ganymede's poles, shimmering curtains of light that dance across the moon's thin oxygen atmosphere. Callisto, another of Jupiter's large moons, likely harbors a subsurface ocean as well, though this water remains mixed with rock and ice in a slushy layer rather than forming a distinct sea. These ocean worlds represent a fundamental shift in our understanding of where life might exist. Traditional searches for habitable planets focused on worlds that orbit within the narrow zone where liquid water can exist on a planet's surface. Ocean moons expand this concept dramatically, suggesting that habitable environments might exist throughout the outer solar system and around countless other stars. The energy needed to maintain these hidden oceans comes not from starlight, but from gravitational heating, tidal forces, and radioactive decay within rocky cores. The chemistry of these subsurface oceans offers intriguing possibilities for life. Hydrothermal vents on their seafloors could provide the energy and nutrients needed for biological processes, just as they do in Earth's deepest oceans. These underwater hot springs create oases of warmth and chemical activity, supporting ecosystems that thrive without any energy from the sun. Microbes around Earth's hydrothermal vents feed on chemicals like hydrogen sulfide and methane, converting these compounds into energy through processes that could easily occur in alien oceans. The discovery of ocean worlds has profound implications for life throughout the universe. Nearly every large moon in the outer solar system shows evidence of subsurface water, suggesting that ocean worlds might be incredibly common around other stars. Red dwarf stars, which make up 75% of all stars in our galaxy, could host systems filled with frozen moons, harboring hidden seas. These ocean worlds could remain habitable for billions of years, far longer than surface oceans on planets that depend on their stars' steady energy output. The water in these distant oceans connects directly to the water flowing through our own bodies. Every molecule of water on Earth, whether in our cells or in the deepest ocean trenches, originated in the same cosmic processes that created the hidden seas of Europa and Enceladus. Comets and asteroids delivered water to the inner solar system during the early bombardment period, while the same materials accumulated in the outer regions to form the ice-rich moons we see today. The hydrogen in water formed during the first few minutes after the Big Bang, while the oxygen was forged in the nuclear furnaces of ancient stars that lived and died before our solar system existed. These ocean worlds remind us that life's requirements might be far simpler and more flexible than we once imagined. Darkness, cold, and distance from a star do not necessarily mean lifelessness. Instead, they might harbor the most extensive and long-lived biospheres in the universe, hidden beneath protective shells of ice that shield them from cosmic radiation and asteroid impacts, while preserving their precious water for geological ages. The next generation of space telescopes will peer deeper into alien atmospheres than ever before. The James Webb Space Telescope can already detect water vapor, carbon dioxide, and other molecules in the air around distant worlds. Future telescopes will search for oxygen, methane, and other gases that living creatures produce. When we find these biosignatures together in the same atmosphere, we might be looking at the first confirmed signs of life beyond Earth. Scientists plan to build telescopes with mirrors larger than football fields, assembled in space from lightweight segments. These giant eyes will capture enough light to study planets orbiting nearby red dwarf stars. The closest potentially habitable world, Proxima Centauri b, sits just over 4 light-years away. Future telescopes might reveal whether this rocky planet holds water, clouds, or even seasonal changes that suggest a living world. The search extends beyond single planets to entire star systems. Some telescopes will watch for the dimming patterns that occur when multiple planets cross their star's face. These transit surveys will map thousands of planetary systems, revealing which types of stars host the most Earth-like worlds. Red dwarf stars, which burn for trillions of years, might nurture civilizations that develop over timescales we can barely imagine. Artificial intelligence helps astronomers sift through the vast amounts of data these telescopes collect. Machine learning algorithms can spot subtle atmospheric signatures that human eyes might miss. They they analyze the rainbow of light from distant worlds, searching for the specific colors that oxygen, water vapor, and organic compounds create when starlight passes through alien air. Each spectrum tells a story about wind patterns, cloud formations, and chemical cycles happening on worlds we may never visit. The most ambitious projects involve networks of telescopes working together across space. These arrays will combine their observations to create images sharp enough to see continents and oceans on nearby exoplanets. We might glimpse the pale blue dot of another Earth, complete with white swirls of clouds and the dark patches of vast oceans. The first photograph of another living world will mark a moment as profound as seeing Earth from space for the first time. Radio telescopes continue their patient listening for signals from intelligent civilizations. They scan millions of stars simultaneously, searching for the narrowband transmissions that only technology can produce. The Breakthrough Listen project monitors nearby star systems for any artificial signals, while other programs search for powerful laser pulses that advanced civilizations might use for interstellar communication. Future missions will send tiny spacecraft to the nearest star systems. These robotic probes, no larger than postage stamps, will ride on beams of laser light to reach speeds of 20% the speed of light. The journey to Proxima Centauri would take just 20 years instead of thousands. These miniature explorers will photograph alien worlds up close and beam their discoveries back to Earth across the interstellar void. The search for life connects every discovery we make about distant worlds. Each new exoplanet teaches us something about the conditions that allow life to emerge and thrive. The hot Jupiters show us how planetary systems can evolve in unexpected ways. The super-Earths reveal new possibilities for rocky worlds with thick atmospheres. The tidally locked planets demonstrate how life might adapt to eternal day and night. Every ocean world we discover, whether orbiting Jupiter or floating free in interstellar space, expands our understanding of where life might flourish. The universe contains more water than we ever imagined, locked in ice beneath countless moons and flowing in hidden seas that never see starlight. life might be far more common and resilient than we dare to hope. The cosmos holds its secrets gently, revealing them slowly to patient observers who peer through telescopes and listen with radio dishes. Somewhere among the hundreds of billions of stars in our galaxy, other worlds spin quietly in their habitable zones. Their oceans reflect the light of alien suns, while unknown creatures swim in depths we can only dream about. The search continues through the long nights as telescopes scan the sky and computers process endless streams of data. Each photon of light that reaches us from distant worlds carries information about alien skies, foreign weather patterns, and atmospheric chemistry that might include the breath of living things. We stand at the threshold of answering humanity's oldest question about our place in the universe. Tonight, as you rest under Earth's protective atmosphere, remember that countless other worlds drift through the cosmic dark. Some harbor vast oceans beneath shells of ice. Others bask in the gentle warmth of red dwarf stars that will shine for trillions of years. The universe cradles these worlds in its vast embrace, each one a unique experiment in the possibilities of existence. The search for life among the stars reflects our deepest hope that we are not alone in this beautiful, infinite cosmos. Somewhere in the darkness between the stars, another world spins peacefully through space, perhaps home to creatures who also wonder about distant lights in their night sky.